Welcome to this week's lab on interference. We're going to be, in our first experiment, characterizing the spacing of a diffraction grating. So what we're doing is we're using a green laser here, shining it through a diffraction grating, and to determine the diffraction grating spacing, which is d in our equation, d equals L lambda over x. So we would need to know L, which is the distance between the diffraction grating and our back plate here. We need to know x, which is the distance between our central maximum or central peak and our first diffraction peak, which occurs on both sides. We're going to be using the average value there. And we need to know lambda, the wavelength of light. And that's the whole point that we're using green light. It's monochromatic. It has a single well-defined wavelength. So we have everything we need to determine the diffraction grating spacing that we're going to be using in the next experiment. So now we're ready for experiment 2, continuous spectra. So we're using the same diffraction grating that we found the spacing of in experiment 1, but now we're using white light, which contains the entire visible spectrum. So now we're going to try to determine the wavelengths using our same equation, d equals L lambda over x, determine the wavelengths of both red and violet light, which are going to show up with diffraction peaks at different points because they have different wavelengths. So we know our diffraction grating spacing from the first experiment, we know our distance L here, and we're going to measure the x value so that we can compute lambda for each of the different colors. Now for experiment 3, diffraction patterns in molecular structure. So this is reminiscent of Rosalind Franklin's measurements using X-rays to determine the double helical structure of DNA. Today's experiment, we're just using a single helix from a light bulb filament, and those regularly spaced turns in the filament are going to simulate a diffraction grating. So the first thing that we need to do is recharacterize that diffraction grating spacing. So using our familiar equation by now, d equals L lambda over x, we're repeating the same procedure that we had in experiment 1, where we have our distance L. We're going to be looking for the distance between the central peak and the first diffraction peaks. That's our x value. And we're back to using green light with a well-defined monochromatic wavelength, so we can compute the diffraction grating spacing d. Now once we have that, there's one more element that we need to ultimately compute the pitch and radius of the helix that we're after, and that is this angle here between the two different diffraction patterns that forms the x. So once we have that angle and our diffraction grating spacing, we can find the pitch and radius of the helical light bulb filament.